interested in trying to know the research of Professor Kusakabe can get benefit from his talk today. So let me briefly introduce the speaker. Professor Koichi Kusakabe was the professor at Osaka University at the Faculty of Engineering Science until 2018, right? And after that, he moved to University of Hyogo, still in the Kansai area, right? But it is the University of Hyogo campus is in the mountain area, which is quite different from Osaka University campus, which is in the city. So his campus is quiet. It's probably good for people who want to focus on doing research and study, perhaps. Right? So you may like to introduce your campus later, right? Yeah. Okay. And Professor Kusakabe has been my collaboration since basically since I got a chance to send my former students. I mean, the first one was Gagus Sunardianto, who is, I think, joining also through Zoom. And then it was followed by Yusuf Wicaksono and Harfa, who are Yusuf Wicaksono is currently already a postdoc working in Riken, Wako, right? Whereas Harfa, Yusuf Wise is still finishing her PhD. That Professor Kusakabe has moved to University of Hyogo. His supervision to Harvard is done kind of informally, whereas Harvard is now having her formal advisor at Osaka University. So I'm happy to inform you that until now our collaboration is still continuing, and we hope that by Professor Koichi Kusakabe today going to share with you his research. If later there are probably more people getting interested and may like to also look into collaboration with him, you are very welcome. So without further ado, I'll give this microphone to Professor Koichi Kusakabe. For any information that I haven't mentioned, please you can share it yourself.
Thank you very much. Yeah, first of all, I would like to say thank you for the professor and all of the professors in this very important department of physics. Yeah. Today I have this special lecture because of the helps and the support of the staff in this department. I'm very happy to come here again and have this seminar here in this room. So today, I'd like to share with you our activity on the so-called nanographene, and especially for the purpose of realization of hydrogen society. This idea really came from here, I believe. This is because at first when I met Gagus Snardianto, he told me, actually, me, that from now on, the graphene related research should be much focused on the hydrogen related topics. This might be owing to his final goal to contribute to the development in various sense of your country, I think. However, at the same time, this purpose to find the good material for hydrogen society is our own too. So I will focus basically on that topic. However, owing to his visit and the study research on this topic, I have another chance to have much and in a sense a stronger person came from here. As Professor Mazidi introduced, Yusuf Richardson joined us, and he is now the expected person even in the bigger group theory in Riken Wako. So let me introduce just my name, Koichi Kusakabe, currently professor in University of Hyogo. Since I moved to University of Hyogo, I now been invited professor of Osaka University. Yeah, let me introduce just the place of Hyogo Prefecture in Japan. As you know, in the island, you know, the Tokyo is here, Osaka is here. The Hyogo Prefecture is just aside of Osaka and Kyoto. And among many prefectures, Hyogo Prefecture is actually rather big, and population is something like that. We have several important places, spring hots, the hot springs, and this one is very special site of the old Japanese castle, the Himeji Castle. And also, you might know the name of Kobe here. As such, Hyogo has many location sites interesting for many visitors and also for us. Our university is now having many campuses like this. Among them, we in science positioned here, rather in mountainside. You can see the engineering in Himeji. This is the second largest city, Hyogo Prefecture. In the biggest city of Kobe, yeah, we have another big campus for commerce. This historical reason, there is a historical reason why we have so the spreading campuses. However, you can see the all around Hyogo Prefecture, we have some of the many of the campuses. This is our campus. We are in the Department of Material Science. Since the Graduate School of Science has now two big departments. One is material science and another life science. There are their own
direction and the purpose aims. For our material science, we have very important aim to develop the various new fields in basic science. So we are composed of the mathematics, physics, and chemistry. Since these are the very basic but important sciences can create new the fields of science. So this is the basic strategy. However, why we are in the mountainside? The very important reason is our location. The campus location is just close to the biggest soul ring, the named Spring 8, the very close from our campus. So this one is focused on the measurement. So experimental science is the major aim. However, by combining the basic science and experimental science, we hope to have a new direction, new developments in various fields. So this is our strategy. At the same time, we use various types of computational science. The supercomputing is one of them. And also we use the artificial intelligence in many ways. So by combining also the computational science to the basic science, we are conducting new developments. So let me just briefly introduce myself. As Ajiz Sensei, let me call him as Ajiz Sensei. I obtained the degree from University of Tokyo. After that, I moved at first to the ISSP, Institute for Solid State Physics. Then I moved to Niigata, Osaka, and finally arrived at the University of Hyogo. My main major was and is the density functional theory for the strongly correlated electron system. Currently, this the purpose is basically realized, and as you might know, the fundamental methodology is widely used in many theory groups, and the contributions are growing very rapidly. So using this style of research, we can contribute to the science and especially physics and chemistry of graphene. I contributed to this very important textbook, edited by Professor Enoki and Professor Ando from Japan. However, this possibility was studied from my very old research work on the so-called strongly correlated electron system in low dimension. This is one of them, and I had a very great work on the proof for the completeness of the phase space of the one-dimensional Hubbard model that is expanded by conjecture. So in that sense, I have some experiences on mathematical physics. This is one of the reasons why I could be the staff member for this applied mathematics in our the university. Really, there is the historical reason why condensed matter physicist can be applied mathematician. In Japan, often the condensed matter physics is named after this the terminology called Oyo Sugaku in Japanese, maybe translated as applied mathematics. So in that sense, we use our strategy based on mathematics to physics, but this application can be expanded even to the fields of chemistry. So that is our current strategy. Our group member is not so many. However, we have a very strong young assistant professor, staff member, Dr. Motoharu Kitatani. He is a specialist for the superconductivity. So we have several of these students, very highly talented, I believe. One of them, Mr. Koichi, is currently focusing at the biomaterial, the protein. Yeah, he applied his technique of density functional theory for the really the material for the the bio physics, and so owing to his success, he just obtained the JSPS fellowship for young scientists. We have many collaborators from many universities worldwide and also in Japan. Our important collaborator is from University of Indonesia here. Professor Kitatani has his big connection to the very famous technical university, Bean. So we have now the many types of topics, but basically given our research work is driven by the density functional theory. That field might be now renamed as materials informatics. Actually, the methodology coming from informatics is applied in various sense in material science. As you might think, this name, terminology, started from information science or informatics in chemistry. So representative ideas might be exemplified by the development of smiles or molecular descriptor, something like that. However, currently, the much the accurate and very precise description is now used. Or even the data-driven science is included in material informatics. So we sometimes refer to the big database of Cambridge, something like that. This kind of direction is now developed by the many companies in manufacture. The representative examples would be by Asahi Kasei or Sumitomo Kagaku. These big companies from Japan is very famous for their contribution for the materials informatics. This direction is actually true in our society. As an example, we can refer to the next JST Presto big project. This Presto is focusing at the coming new future innovation from the new ideas. So one of them is actually this one, advanced material informatics. In this Presto project, headed by the supervising Professor Shinji Tsuneyuki, the very basic concept is collaboration in between theory, experiment, and computational science, also the data driven the methods. So combining these fields and finding a new strategy, then we can hope to have very new and new solutions. Yeah, based on the development and the synthesis of material. So we are now in this direction. Actually, it is the interdisciplinary field. I hope to expand and much strengthen by finding many new collaborations in worldwide sense. So you might think that the name terminology of material informatics would not only focusing on theory, but much now used in experiment. One of the examples would be the introduction of robotics into the many types of labo. This is actually the motivation the found from the material informatics. If we look at this highly efficient and very strong methodology, is however based on the measurement, and as a result, the measurement of physical property, since it is involving the quantum observation, we finally need to understand the physics, chemistry in the atomic scale levels. So there appear one caution. The experimental data obtained by such measurement should be always realized by quantum information transfer. It means that if you observe some physical quantity of targeted material, it will affect the observatory or experimental facility itself. That is the transfer of quantum information. We need to understand that from the very basic science. At the same time, the material informatics might remind you again the computer science conducted in the scale of atomic level. Our field is from here. Interestingly, very recently, the people believe the results from the density functional theory be comparable to the measurements from the real material. So this field, material informatics in computational science, is treated as a kind of experimental science. So in such a sense, we again find another the phases of quantum material informatics. That is, we use some kind of modeling and simulation techniques. However, that is realized in artificial system. That system might be controlled by quantum mechanics. So we here need to adapt additional caution. That is, such kind of the simulations inevitably biased by artificial modeling. So we need to be very, very carefully use this technique, very brand new one, and that result always to be corrected to have a final answer. So as very basic strategy here. We cannot escape from the real collaboration. We need to have cooperation in between the experiment and the computational science. However, once it successfully works, we believe the next point, when the real observation and the simulation result is adjusted or nearly the same, then we can believe everything. In that sense, new discovery should be come from the real understanding of natural science, starting from the quantum mechanics. That is our strategy. So we now conduct this collaborative research by performing the quantum simulation. That is our point. So here I want to show a little old example, but maybe, sorry. It works. Yeah. Maybe one example showing the correspondence in between the experiment and the simulation. Please look at this picture. Here we have the so-called pure graphite, HOPG. This is installed in the diamond double cell. Now the pressure increases. You will find that the graphite change into diamond phase. Yeah, you can see the uncolored parts, the coming out, and then finally the whole parts become transparent. It actually means that the graphite change into diamond structure. Let me introduce the next old simulation to reproduce this phase transition in simulation. That is structural transformation of graphite into diamond. Using first principles type DFT calculation, we can show you result from the so-called first principles molecular dynamics. Starting material is graphite. Now it would be zoomed. You can see the layered structure. Actually the graphite, as you know, is the layered material. Each of layer is composed of the hexagonal network of carbon atoms. White spheres are carbon. Here we since we use the quantum simulation for electron system, we have this colored object representing the electron density. You can see electron density connecting the two the neighboring carbon that is coming from the covalency, covalent bonding. So let's apply the pressure at finite temperature. You can see some vibrating motion coming from the temperature effect. However, at this pressure range, the graphite keeps its the layered structure as it is. Actually, in real experiment, if we compress the graphite isotropically, it keeps the structure even at known highest value would be 40 gigapascal. However, here we use finite temperature simulation, and a little increase in pressure will create, you can see here, the new bonding in the perpendicular direction. The new connection created, as a result, you can see the new the network, carbon network, and it is coming from sp3 bonding So it is identified as the so-called hexagonal diamond phase. Of course, this old simulation shows one example only. Now the people try to find how accurate the current technology is. So to check the power of quantum material informatics, we can see, we can show the next example. I told you that the last experiment by using HOPZ. However, if you use the scanning electron, the microscopy, you can find that even HOPZ is imperfect, or rather crystal structure is so distorted. As far as we know, the highest quality of graphite sample is coming from the Kaneka company in Japan. If you look at this, the experimental data, you can see the very good the stacking layer structure of graphite, fabricated above using the temperature above 2,800 degree. Using this sample and applying the newly built the measurement technology, so-called picosecond laser ultrasound spectroscopy, we can determine the at first the velocity of phonon mode. Using that velocity of phonon mode, we can finally determine experimentally the so-called C33, the elastic constant in the C direction. You can see the value is even over 50 gigapascal. This value is really astonishing. Historically, the value was known to be less than 40. However, if you fabricate the best sample using high quality measurements, we can see the real value of C33 of graphite. We refer to this value. To compare with this value, we needed to use new types of technology in theory too. This one is that result. Yeah, you can see the horizontal axis being the strange value of U. Some of you know that when the theory people in condensed matter physics show a value of U, it means the so-called electron correlation effect. So that let me tell you that the meaning of the U equals 0 case. Actually, U equals 0 case is given by so-called RPA calculation. RPA introduce the long-range correlation effect. We need to introduce U to actually find the comparable value to this best observation. So for that, we need to introduce the value of U to be 2 electron volt. This value is interestingly rather reasonable for the graphite sample. We call it the so-called plus U plus RPA. Owing to this adjustment, we believe that even for the simple graphite, we need to consider every kind of electron correlation effect. the result is summarized in this table. Actually, the development in experiment and also theory. Now, okay. Thank you. Yeah, both of the developments required. The final value is given by our experimental group, the conducting picosecond ultrasonic, and our group of theory, using the new RPA plus U calculation. The direction of our theoretical research is not only to reproduce the reality, but once we have reliable simulation technique, we can apply it to find unknown phenomena, unknown material, or even design new superconductor. That example is given by Dr. Teranishi from Osaka University. He used this type of technique and found several of the new material structure. The one important point is using fluorine, but also the considering the change in the electronic structure. So from that, he actually succeeded in proposing unknown cuplet superconductors. Another direction is, this one is much focusing at the basic science, actually given by Dr. Sunarjianto from UI. His motivation to contribute to the hydrogen society succeeded in the finding of this phenomena. Yeah, interestingly, you can see a desorption of hydrogen molecule from this kind of specially proposed hydrocarbon material. I'm now focusing at this the project. The Gagus succeeded in finding this very optimized and really optimal material structure, showing lowest excitation energy, that is energy barrier found in the energy, the potential energy surface, the connecting from the dehydrogenated the initial state to the hydrogenated final state. The both initial and final is nearly the same along the energy direction. So it shows, it telling us that if we use that material, we can solve one big problem in hydrogen-related material, that is the known best material of toluene. Yeah, hydrogenated one is methyl cyclohexane. There appear the energy difference. Yeah, so using the known hydrocarbon, we have the very big problem of energy consumption. When we need to use hydrogen from hydrogenated material, we need to expense energy, the size. However, using his material, there's essentially nothing. And also, his material shows the best fitted energy barrier, in between the final and the initial state. So we can propose it to be used for hydrogen storage. We proceed to the next stage. Yeah, once hydrogen storage is possible, it means that we realized cracking of archon. So his structure can be used to crack even the known archon molecule. So starting from, for example, normal octane, this type of hydrocarbon can dissociate, actually the break the bonds in between carbon and create the very useful material like propene and pentane. Finally, we can find the appearance and production of hydrogen. So using this the strategy, we can say the next thing. Starting from the initiation by Dr. Gagus, we now can be say the next thing. This is a type of activated carbon. So even using just activated carbon only, we can hope to have hydrogen storage and also hydrogen production method. Yeah, here, however, there are remaining many barriers to be used in real society. However, we can say that this kind of the efforts can in near future contribute to realize hydrogen society. This is just a motivation. However, at the same time, his result actually contributed to deepen our understanding of the chemical reaction. That means that the physics and chemistry of nanographene had been actually opened for us. Why such a special structure is so unique? There is a reason. I here write some the diagram showing the difference in between the open edge structure and the perfect graphene. Yeah, starting from open edge structure, the people had found several of the possible application in the electronics. However, from the viewpoint of chemical reaction, this one is not so good. The actually reason is coming from the distance in between the important hydrogen positions. So from this one, it is not so easy to dissolve the hydrogen molecule. However, if you look at much smaller size of defects and going through this just atom defect, but going to the hydrogenated vacancy, that is called V111. There, we have a special structure that allows us to see the very closely the positioned hydrogens. From that structure, desorption of hydrogen easy, adsorption of hydrogen also easy. So this is the strategy and real mechanism found in nature. In that sense, this structure is very unique. To realize this catalytic activity of vacancy of graphene, however, were successful because of the realization of next very big collaboration. Yeah, you can see these people who are contributors to this innovation, that is the newly found catalytic material for hydrogen society by three physicists, sorry, and two of chemists. So combination of the chemistry and the physics is actually the hidden secret points of our successful results. So now we had proposed the possible solution for hydrogen storage and also hydrogen production. If you need to enhance the reaction, we can also consider the nitrogen doped nanographene. In that case, we see only the appearance of energy barrier below 2 electron volt. So this is really realizable. Since we have these data, we can say that several of the experimentally reported activated the reaction using just activated carbon fiber from chemistry department of Tokyo University in 1960s is actually possible. That is one direction of our development. But let me go back to the last view graph. From another side, we have another possibility for this atomic layer material, the graphene. Many people had focused on the application of graphene for electronics. Actually, we contributed to find some of the important effect and nature of graphene. One of them is appearance of zero energy edge mode, so-called edge state. This edge state were identified by our old theory with theorist from Tsukuba University. However, you might remember the next example. When people look at the atomic vacancy of graphene, people actually astonished to find the reports of Kondo effect. Actually, it was somehow solved theoretically. However, this structure is a little bit, how to say, the uncontrollable from the point of view of quantum information technology. We again look at this last V111 structure, where we see the realization of a single electron spin localized at this atom defect, hydrogenated. Using this special structure, we had already proposed the application of this material for the so-called measurement-based quantum information technology. That is the qubit, creation of qubit, starting from the electron spin. Another one is can be a big proposal. That is this graphene structure is very well known to be the outstanding material structure showing Dirac electron. However, people cannot create and control the Dirac points. If we can create the gap, energy gap at the Dirac point, we can use it to create a new electron device. Actually, we can show the successful story of Yusuf Wijaksono in the next view graph. The effective Hamiltonian of graphene is often written in this form. In any representation, you will see the zero value in the diagonal position. This is coming from the specialty of graphene. fabricated only by carbon atoms. However, if we can somehow break this symmetric the Hamiltonian structure somehow, we immediately create the gap, energy gap in graphene. For that purpose, the very successful proposal was done by Vishak Sono. He introduced the broken chiral symmetry using the special structure realizable in nature. Before that, we want to mention another the story for the zero energy edge state. The started from our old, very old one. This direction had succeeded in finding many types of topological edge states. So topological quantum effect can be found in various types of the graphene structure. That is basic understanding. However, people couldn't a good example showing broken chiral symmetry. The Vishak Sono found the next structure is the best candidate. He considered sandwich structure of graphene by the nickel, metal, but nanostructures only. Such the sandwich structure had been found in nature by the group of Indian experimentalists. So it's possible. He carefully did the simulation using this interesting system. We have two of the microscale magnet. This is because we consider the nickel. Then the polarization can be changed from parallel, pole n upwards for both of the nano magnets, or anti-parallel configuration. The upper one has the one polar direction. The other side is in the opposite direction. By changing this the magnetic moment direction, he realized the control of the Dirac point, or the gap of the Dirac electron. When parallel configuration is chosen, there is no gap. So the graphene keeps its metallic nature. However, if he switch to the anti-parallel configuration, there appear the broken chiral symmetry, and then graphene behaves as if it were insulator. So change from metal to insulator is actually the big effect, and as a result, his simulation told us that possible MR ratio, magnetic resistance ratio, can be over 3,000. This comes from the broken chiral symmetry. So he said the graphene can show ultimate TMR. This is one of his results, a recent one. We have another very big name from here UI. Her name is, as Aziz Sensei introduced us, the Harima Harfa. She succeeded in finding another interesting electron correlation effect. That is the so-called the cross correlation. Using the electric field reversal, but she succeeded in controlling the spin current direction. So using this one, she proposed the new spintronics device, realization of cross correlation. recently, Yusuf-san, moved to Riken and started his new research. This is one example. Why I want to show this example here is actually the design of new material can change the old prejudice in a sense, in some case. He considered promoted by and actually supervised by a very famous theorist in Japan, Sadamichi Maekawa. The Professor Maekawa proposed him to consider this structure of kappa nitride. We consider just kappa, pure kappa and the kappa nitride, but the simulation by Wisaksono found the next very big value of the alpha parameter, representing the Rashba effect. This gigantic Rashba effect is astonishing because the other example showing the similar value is only coming from the heavy element only, without heavy element, but he succeeded in finding the Rashba effect, controlling the interface and also surface. Such microscopic effect can be proposed purely by theoretical simulation. So we hope this designing technique can be applicable for many effects and chemistry too. So these successful story had been realized, I believe, only because of our the great collaboration. So I hope to strengthen and continue to keep this important connections in between Indonesia and Japan. Hopefully, you can join our project. Although we are living in mountainside at present, this is a picture of Nishiharima. You can see several mountains when we approach to our campus, go through the tunnel. Yeah, we arrived at the really new world, completely different world. And we are now approaching to our campus. Yeah, here over the forest. Suddenly, this building appear. This one is the Harima campus for you. I hope to have you visit in near future because you can see this place is actually very close to the this ring, Spring Gate ring. So if you have the collaboration in between experiment and theory, please consider our campus. And also, we hope you to enlarge your field of science. Yeah. So this is the final message from me for today. I want to say only this single word, terima kasih. Yeah, for everyone. Thank you very much.
Yeah, I guess it's now time for questions. If there is anybody who may be interested in asking for any clarification for anything that you feel not clear enough. Anybody from this room? Yes, Nasir.
Thank you very much, Professor, for the informative speech. My name is Nasir. I have been working on this field of graphene, maybe almost 1 year, but that is totally different thing. It's experimental. So, yeah, I guess you already can guess my questions. The graphite that we use, I think slide 8. It was slide 8 or 7. So in that first question, I think slide 2, you mentioned your student also, yes, Yasuhiro. You said that he is working on biomaterial and then it converted into graphene. Is he working on theoretical side or experimental side?
You
The-
that
the-
our student,
Yes,
Yasuhiro
doctoral
Oishi.
student.
Yeah, he is a theorist, and actually, but
Using biomass or biomaterial.
biomaterial, because we have big collaboration with the experimentalists.
Yes.
They are the really the controlling and the using biomaterial. However, they use graphene as a substrate to observe the motion and actually the
All the process.
detect. Yeah.
The second thing is to convert because graphite is kind of stacked layers of graphene. So when we apply high pressure,
Yeah.
the graphite layers, I mean the graphene layers which are stacked and then becoming graphite.
Yeah.
When we apply high pressure, you mentioned that we don't need high temperature, or do we need high temperature? You said we need only high pressure. High pressure, and then the layers of the graphene slide, and then that way we can make
the
a
point.
graphene.
Point is, if we want not to use some kind of catalyst or something else, and just apply high pressure only, we need to have a pressure range beyond 10 or something. Usually, in usual experiment. So this 17 gigapascal can be, of course, usually achieved if you use the so-called diamond amber cell, but not using that, it might be a little difficult in a normal experimental condition. However, if you increase the pressure beyond maybe 16 or something, yeah, you will find the diamond structure.
Yes. The last question, the graphite that used was, because you mentioned your student also, he is working on biomaterial. The experimentalist used the biomass and biomaterial graphite,
Yeah.
or graphite from industry. Because there is a
yes.
huge difference between the graphite that we obtain from biomaterial and from industry.
Right.
There is
Exactly.
a huge difference.
Yeah. Huge difference. Thank you very much.
Thank you.
Actually, there are various types of graphitic material, and actually, if we propose this work is to propose a good measurement method of method detecting the biomaterial like virus or something, using that graphene as a part of detector. For that purpose, best graphite is inevitably used. Yeah, such kind of HOPG would not work perfectly, and even the graphene oxide or something, oxidized graphene or something would not correctly work. So depending on your purpose, we need to choose which one is best. Thank you very much.
Yeah, thank you very much, Nasir, for your question, and thank you very much, Professor Kusakabe, for answering the questions. I would like to have, more person to ask question.
Thank you very much, Sensei, for your outstanding presentation. I would like to ask, well, you did mention a unique solution for quantum computations by zero-edge modes, correct? And I was wondering that whether zero-edge modes are related to qubits or quantum bits. Well, would you mind give us a further explanation? Thank you very much.
Thank you very much. If you had interested in this direction of the possible future application, This is a current research topic for us. And we are considering isolated graphene, but nanometer scale, having this type of the atom defect, the controlling the position of atom defect. We can create really the so-called quantum information resource for the quantum computation. It works as if it were a kind of Heisenberg spin system. Yeah, we can even create the higher spin system like spin S, total spin S, 3/2 or something. Starting from that, once we can propose, and actually we believe that we had already successfully proposed. If we create the two-dimensional network of spin 3/2, then it works the very famous AKLT spin system, Affleck Kennedy Lip and Tasaki special spin system. It can be used for the measurement-based quantum information technology. Yeah, that is our strategy. Why we focusing at such nanomaterial is because there are many possibility hidden. Yeah, thank you very much.
Thank you very much.
I'm actually interested to continue his question on that thing. In your illustration, you're showing that red atom. What is that actually?
Red.
Yeah.
This one is not the atom, sorry, but this is electron orbital, localized electron orbital.
Okay.
Yeah.
So you can create effective spin of 3/2.
Yeah.
Using that vacancy?
Yeah, but the location of perfectly controlled. Yeah. Depending on the precise atom, the structure of this material, one of them behaves as if it were the spin system.
I see. Interesting. Okay. Yeah. Any more questions? I think it's time for us to give the chance to people in the Zoom. Is there any, person who may have put his or her question? Otherwise, I would like to offer Professor Jarwani, if you are still there. Ujar? Udah nggak ada? Oh. What about Gagus and Yusuf? Are you still there? You may have, I don't know, you may have comments or I don't know, whatever.
Halo Pak Ayis.
Ya, bisa disuarakan.
Halo.
Yes,
halo Pak Ayis.
Ya, silakan.
Actually, I don't have any question, Pak Ayis. I just would like to thank you for my former supervisor, Pak Ayis, and also Prof. Koichi Kusakabe for your guidance. So, all the presented here is I understand. So I don't have question. Just would like to thank you very much.
Okay, thank you very much, Gagus, for your expression of.
Selamat sore, Pak Moderator. Selamat sore, Pak. Pak Moderator.
Profesor Kusakabe. Any more question?
Pak Moderator.
Ya.
Saya Utama Kayo dari HIMNI, Pak. Utama Kayo, Pak. Utama Kayo.
Ya, Pak Utama, silakan. Bisa dilakukan bahasa Inggris atau bahasa Indonesia? Boleh.
Gini, saya tidak punya pertanyaan. kepada Profesor. Saya hanya mengharapkan Pak Gagus atau Pak Wicaksono bisa membantu mengelaborasi dalam bahasa Indonesia untuk menutupi tadi kekurangan-kekurangan dari penjelasan beliau dalam bahasa Inggris, terutama hasil penelitian Pak Wicaksono. Bisa dibantu Pak, mengelaborasi singkat.
Ya, Yusufnya ada nggak di sini?
Pak Yusuf Wicaksono atau Pak Gagus?
Yusuf, mohon maaf ini ada request dari Pak Utama. Kalau Yusuf bersedia mengelaborasi dalam bahasa Indonesia katanya.
Ya, takutnya tadi saya
bagian yang terkait dengan
ya.
tadi pemaparan Prof. Kusakabe terkait riset Yusuf.
Assalamualaikum.
There's a request by an audience asking for more elaboration in bahasa Indonesia. So I'm asking Yusuf San. Silakan Yusuf.
Halo, Assalamualaikum.
Wah, senang sekali nih Pak Yusuf tampil nih, senang sekali.
Ya, terima kasih Pak. Kira-kira bagian mana yang bisa saya elaborasi Pak mengenai?
Singkat aja Pak, secara menyeluruh Pak. Saya takutnya tadi ada salah dengar saya dari Profesor.
Oh gitu. Ya, jadi saya sendiri melakukan risetnya di bagian mengatur topological properties atau sifat topologi dari grafin dengan mengontrol sistem Dirac-Kohn, kerucut Dirac dari grafin itu, dan kita bisa mengaplikasikan dengan mengubah kerucut Dirac itu jadi yang pertama yaitu dengan membuat simetrinya dijaga sehingga kerucut Dirac-nya tetap ada dalam sistem grafinnya, atau dengan mengubah sifat topologikalnya di mana simetri chiral dari grafin rusak dan kerucut Dirac itu menjadi terbuka. Dan karena kerucut Dirac itu menjadi terbuka, maka sistem dari grafin itu berubah, yang tadinya half metallic maka menjadi mempunyai gap di Fermi energy dan merubah sistemnya menjadi semikonduktor atau insulator. Dan tujuannya itu sebenarnya kami ingin membuat device, yaitu memory device, di mana dengan mengutilitas sifat topologika dari grafin tersebut, kita bisa membuat device berdasarkan grafin yang sebelumnya itu tidak bisa kita aplikasikan di device-device sebelumnya, gitu Pak.
Makasih Pak.
Nah ya, sama-sama.
Wah, melengkapi. Ya, Pak,
Bagaimana Pak Utama?
Ya, Pak Gagus ingin menambahkan nggak Pak Gagus?
Apakah cukup
Pak Yusuf
dijawab?
sudah cukup, Pak Gagus mungkin mau menambahkan.
Assalamualaikum Pak.
Ya silakan Pak. Ini mantap nih. Ini
Iya,
bisa.
iya.
Ya.
Ya jadi terima kasih sebelumnya Pak Utama Kajo ya ini ya dari sini. Terima kasih atas pertanyaannya. Jadi untuk memudahkannya hanya gini sih penjelasan yang bagian penyimpanan hidrogen ya Pak ya tadi ya.
Iya
Jadi,
betul Pak.
di awalnya kalau misalnya single grafin itu kalau misalnya direaksikan dengan hidrogen molekul itu biasanya reaksinya akan lemah gitu Pak. Jadi kita perlu memodifikasi si surface dari grafinnya itu dengan membuat term single vacancy itu satu kekosongan atom karbon gitu. Jadi satu atom karbon dihilangin. Nah kalau di eksperimen biasanya bisa di argon irradiation ya sekitar 100 elektron volt gitu. Nanti satu atom karbon itu hilang, jadi kan tercreate itu satu atom kekosongan atau disebut dengan vacancy. Nah setelah ada satu atom kekosongan atau vacancy itu jadi reaktif Pak, karena di situ ada dangling bond gitu. Nah setelah ada dangling bond maka hidrogen akan masuk terdisosiasi. Jadi hidrogen molekul itu bisa breaking the bond, jadi ikatannya akan putus, kemudian akan terabsorpsi di grafin, di permukaan grafin. Nah, dengan modifikasi struktur yang tadi ya di slide presentasi itu, kita bisa menghasilkan reaksinya itu reversible. Artinya reaksinya itu bisa terabsorpsi, dan juga bisa dengan mudah terdesorpsi gitu dengan perbedaan energi antara di initial state di keadaan awal sama final state keadaan akhir itu akan sama gitu. Sehingga reaksinya tidak hanya bagus untuk penyerapan hidrogen tapi bagus juga untuk pengeluaran hidrogen dari permukaan grafin, sehingga harapannya nanti bisa digunakan sebagai media penyimpanan hidrogen yang bagus. Itu Pak, kurang lebihnya begitu.
Luar biasa Pak Agus. Senang
Sama-sama.
sekali nih saya mendengarkan, bagi saya ini makin sempurna dari uraian profesor tadi. Profesor siapa Pak?
Prof. Koichi Kusakabe.
Siapa Pak? Ulang Pak.
Koichi Kusakabe.
Koichi.
Ya, dari
Ya.
Hyogo University.
Ya.
University of
Professor Koichi Okabe, thank you very much for your very excellent presentation. And then the two young gentlemen already give me more complete information. So give me chance to learn from you also about this very useful technology. Thank you very much. Hope see you in your beautiful location. Very nice, a very beautiful campus in Japan. Pak Moderator, terima kasih Pak, luar biasa Pak.
Terima kasih Pak Utama. Terima
Ini
kasih
anak
atas
muda,
pertanyaannya,
saya tidak bertanya Pak, saya minta diberikan pembelajaran yang lebih baik.
Ya, ya. Berarti pertanyaan yang malah jawabannya panjang itu tadi Pak.
Iya, waduh, luar biasa anak muda kita ya Pak.
Ya, terima kasih.
Luar biasa, terima kasih.
Mungkin saatnya saya menjawab, ada pertanyaan tertulis ini di Zoom ya. There are several questions on Zoom. The first one is from Dr. Dwi Nanto. So what is the most important hydrogen storage enhancement based on nanographene strategy? What's the most important hydrogen storage enhancement? Maybe enhancement in terms of the capacity of storing. That's really what he means. So I mean,
Really speaking, it is ongoing problem. We are now developing. So current most difficult point, for example, is how to fabricate this structure in a manufacture. It is very difficult actually. So that is current.
what about
bottleneck.
theoretically? What can theory predict how much we can store hydrogen in using graphene?
Best or the largest amount is the 1 hydrogen per 1 carbon.
Okay.
Yeah.
Is it possible to make two? I mean, like top and bottom.
Yeah, I mean that if we consider the top and bottom, the most the one is 1-to-1 because one carbon move upwards, another move downwards, and having two, one, two, 4, 2 carbon. So 1-to-1 is the largest.
Yeah. So I hope that answers Dr. Dwi Nanto's question. So theoretically, we may be able to store hydrogen up to ratio of 1 hydrogen for 1 carbon atom. But experimentally, it is still a big challenge to realize it, right? Yeah. Still in ongoing research. So maybe Dr. Dwi Nanto has another question. Cuma satu aja ya? Yeah, okay. So Dr. Dwi Nanto is expressing thanks also to you for your answer. Ada lagi nggak di sini? Okay. Over here, is there some more question? Okay. Good.
Good afternoon, sir. I'm Hamad Ahmed Qureshi from Pakistan and here a student of Masters of Physics. So basically I'm working with PASIs and my research topic is quantum error correction using nitrogen vacancy center qubits. So I'm not really well familiar with this nanographene and this field, but my interest is this, that we can theoretically develop so much models and so much structures. For me, for quantum error corrections, we can build circuits and some models and schemes. But when we come to the implementation, it's very hard to implement. For me, in NVs, we have some models for, a creation of the states and then implementing it theoretically. But when we come to the experiment, it's very hard to implement. So what about this one? Can it be helpful in the future for implementation of like we can build a quantum processor from this, which can be used on the room temperature? Like already we have from superconducting qubits or trapped or Rydberg atoms, but they need cryogenic temperatures. So there is also a big problem for commercialization. But can this be helpful for future quantum technologies to be implemented on room temperatures?
You mean that if our system is considered for the room temperature use, the use for the quantum computation at room temperature, you mean?
Yes, sir.
Yeah. Are there any problem for us? Yeah, big problem. Actually, the energy scale we are considering is very tiny, actually. So at this moment, we need to have a very low temperature. Yeah, even if we consider the realization, yeah, of this material. After that, if we consider, we consider to use the NMR technique to observe and really realize the computation step. For that, however, noise will come at final temperature from many kind of the environmental degrees of freedom. So we can only say that at this moment, for our system, the first initially requested condition is very, very low temperature. Is that enough for your question?
So before a few days ago, I was reading a journal. So there, someone commented that is quantum computation and the quantum information is a pie in the sky. So if we cannot implement something, it's very hard for us that we are studying, we are working with it, we are spending so much time, money, and everything. But finally, when we come to the implementation, it's very, very hard. And until now, we have not got some breakthrough on the which become a future inspiration for working anymore on it.
Maybe I had better mention the current the most efficient technique used in for example Microsoft or Google. That would be currently best realization. So is that enough for you? Yeah, the really your question, the focus on the real use. Once then, the nearly every, nearly all of the current known technique is efficient in that sense.
Okay, thank you, sir.
Some more question? Ya, ini Radit punya pertanyaan? Ada lagi? Any more questions? Pak Terry nggak jadi sih. Udah berarti saya sendiri dong. Yeah. I think I have to ask once again if there is any more question. Oh, there's one. Okay, good. From high energy physicist.
Thank you, Mr. Aziz, and thank you, Professor Kusakabe. Yeah, actually, I'm not so familiar with hydrogens, but recently I'm working on the Casimir effect, maybe something like a phenomena in the case of vacuum fluctuations of quantum field. Yes, yeah. And in that case, the boundary conditions plays an important role. And in such situations, chiral symmetry and the preservations of chiral symmetry is important. In such situations, chiral symmetry means invariance of the Dirac actions under chiral rotations. And what is the meaning of chiral symmetry in
this,
yes
sense.
I just want to know because recently I found article that connect between graphenes and wormholes where we can discuss Dirac equations in curved space-time. So yeah, maybe chiral symmetry in this context differ from what I use then in my work. Thank you.
Thank you very much. That is really a very important question. And actually, why we use the terminology of chiral symmetry here is because just the analogy. Yeah, analogy. So in graphene, the realization is 2 by 2 the theory for the electron system only. That is effective one. So the true chiral symmetry in high energy physics never broke, of course. However, this one is low energy physics. So the appearance of electron is actually described by 2 by 2 the matrix form of electron effective Hamiltonian. That is sometimes called the Weil Hamiltonian in low dimension. So here, why we consider the name of chiral symmetry is because once it is broken in this sense, interestingly, mass gap open. So the electron change from massless electron to mass gap. So that should cause a very big effect. One of the result is Visaksono's result on the very big, the unknown scale over 3,000 TMR ratio. That is not, as far as I know, not currently known in other system.
Yeah. Yeah, it's true that the course on chirality and terminology that so far we know in high energy physics, it is there in graphene just because we have the dispersion relation that is that forms as a cone, right? Pretty much the same as we find in relativistic quantum mechanics, and the only difference is actually that in the place of c, the speed of light, what we have here is Fermi speed or Fermi velocity, which is much lower compared to speed of light. But just because of the linearity of relations, all the math happens to be equivalent to what we see in the special relativity problem. So therefore, we can conclude all the behavior of Dirac, massless Dirac particles, right, that we see in relativistic can also be observed in graphene, only with the velocity which is Fermi velocity, not speed of light. But the chirality and of course all of this is approximation, because the true cone, I mean the actual dispersion is not really the true cone, right? I mean, it's not really completely straight. If you go a little farther away from the Dirac point, it starts to bend, and it's not really straight. But as far as we only deal with a situation where, I mean, we don't, I mean, if the particle is assumed not to have very, very high momentum value, then this approximation worked well. I guess that's just to add the explanation from Professor Kusakabe. Okay, then as we it's already 3:10, right, in my watch. So if there is no question, let us thank again Professor Kusakabe for his very interesting presentation, and we hope that we learn something at least, yeah, from his presentation. And we thank you very much also to the audience attending this seminar through Zoom. And for those who have participated in asking questions or giving comments, thank you very much. Ada ini? Nanti saya tanya ya. Boleh apa? Kontak saya juga boleh. Nanti kalau memang beliaunya nggak keberatan nanti saya kirim. Would you mind to share your presentation? There's somebody who is requesting to have the. I mean, if you can make it PDF. Yeah. I mean, you can send it to me, then I can send it to him. Okay, in PDF. Oke, ya nanti akan diberikan oleh Profesor Kusakabe melalui saya. Okay. So before we really close this seminar, we have the tradition of giving this sort of appreciation in the form of certificate. Usually, there is an official from representing the department, but since nobody over here now, I've been actually waiting for Professor Terry Bar, but he has to do something else perhaps. So let me just give this to you. So this is the certificate of appreciation given to Professor Koichi Kusakabe in recognition of valuable contribution as speaker in the seminar on nanographene as a strategic material for the hydrogen society, hosted by the Department of Physics, Universitas Indonesia on September 29, 2023, signed by our department head, Dr. Jati Handoko. Let me give this to you and we take a picture. Thank you. Oh yeah. And last but not least, let's do a picture.